Hi everyone, welcome back. So today we're looking at inverse trigonometric functions. And on the screen here I have the summary of the inverse trigonometric functions that we should have developed from trigonometry. So I've also provided a PDF of this document on your Canvas, and you can go there and you can download it, save it on your computer, or print it and have it as a reference whenever it is that we're working with these inverse trigonometric functions. Now, what we want to do is we know how to work with functions, their derivatives, their integrals, and more specifically, if we wanted to find the derivative of an inverse function, according to section 6.1, then we can definitely do that. However, what I want to do in this particular section is I want to start off by saying let y is equal to sine inverse of x. So this is where I want to begin, and again it's just a typical definition for an inverse function. As you can see, y is equal to sine inverse of x is given right here on that screen. All right, they use theta, however I'm using y. Now, if this is the case, then we are able to extract that sine of y is equal to x. Okay, and that's just by using our inverse properties. And those inverse properties, again, are shown on screen. So what I want to do at this time, then, is I want to state a couple restrictions here. Well, the restriction here, we're going to be able to say that the angle measurements for y, in other words, y as the outputs for sine inverse, are going to be bounded between negative pi halves and pi halves. So I want to keep that in mind. Next, what I'm going to be doing is I'm going to be taking a derivative for sine y is equal to x. So right here, I'm just going to say take a derivative for sine of y is equal to x. Now, when we do this, we're going to take a derivative with respect to x. So notice this derivative is not going to be with respect to y, but instead it's a derivative with respect to x. And the reason I want to do this is because on the right-hand side, when I take the derivative of x with respect to x, then we naturally wind up with 1. But on the left-hand side, it's actually a little bit more intricate here. And the reason for that is because we're taking a derivative with respect to x. This means that we need to abide by the chain rule, because y, as we see from the very beginning, is a function that includes x in that function. So we must apply the chain rule, and the derivative of sine of y is going to be cosine of y, but then we multiply by the derivative of y with respect to x. And again, that's a chain rule process. Now, if I wanted to solve for dy dx, in other words, the derivative of y, I get 1 over cosine of y. All right, now this is pretty amazing, and this is where I want to be. Simply because now dy dx, well, that's another name for just y prime, which means that y prime is equal to 1 divided by cosine of y. But as we saw in the previous sections, we don't want to leave the derivative with a function y that has some x embedded in it. Instead, we want to try to find the exact value. So here's what we can do. We can go through and we can start then extracting. We can then start extracting this sine y is equal to x. Now, what does sine y equal to x mean for us? So sine y is equal to x. Well, it'll look different if I say sine of y, and remember, y is just some angle between negative pi halves and pi halves. Sine y is equal to x over 1. And why do I want to do this? Well, according to sine, sine is opposite over adjacent. What that means is that y is my angle in question. And since sine, cosine, and tangent are right triangle geometry or right triangle trigonometry, then that means that we are going to be able to extract this into a triangle, or more specifically, a right triangle. Here we go. All right, and here we are. So here's our triangle. Whoa. All right, so here's our triangle. Now, y, or this angle measurement, is going to be here. So now opposite, that's going to be this side measurement is x, and then adjacent, wow, did I write adjacent? Wow. See, this is why I want to be in class, because I know you all would correct me on that. That's not an adjacent side, it's opposite over hypotenuse. There we go. So the hypotenuse here is going to be 1. There we are. Which means we got to solve for this missing side, because that missing side will then get us cosine of y. So in order to do this, we can then go through the whole process and figuring out what that value is going to be. You can use Pythagorean theorem, and you will be able to find that cosine of y in this particular case is the square root of 1 minus x squared. So when we want to look at cosine of y, that's actually real nice, because now cosine of y is going to be equal to the square root of 1 minus x squared divided by 1. In other words, it's just square root of 1 minus x squared. So, what does y prime actually look like then? In other words, the derivative of sine inverse. Well, the derivative of sine inverse looks like 1 over the square root of 1 minus x squared. Check that out. That is pretty amazing there. All right, so now we're able to see that if we have an inverse trig function, like inverse sine of x, then we can take its derivative. And we don't have to rely on section 6.1 to take those derivatives, because we will be able to take the derivatives for sine inverse. Now, there is a restriction here. The restriction is going to be these x values. So I'm just really quickly going to say this is going to work for the x values that exist between -1 and 1. Okay, so that's an important aspect that we need. And I'm going to summarize that on the bottom of your screen here, where I'm going to say that the derivative with respect to x, and this is going to be for sine inverse of x, is equal to 1 divided by the square root of 1 minus x squared, and this is going to be where x is bounded between -1 and 1. Now, very similarly, if we wanted to go backwards, so if we wanted to apply the fundamental theorem of calculus, we would then take the integral of both sides of this equation that we developed, and we would then get that the integral of 1 divided by the square root of 1 minus x squared with respect to dx is going to be equal to sine inverse of x plus some constant. All right, so that's awesome so far. We've developed this whole process to allow us to say, hey, this is what we're looking at when we're talking about sine inverse. All right, or at least a derivative for sine inverse. So that's pretty amazing so far. Now, you're going to be able to see the rest of them as well. But for now, I want to go ahead and I want to start establishing what are the other derivatives of the inverse trigonometric functions. Okay, so let's go ahead and let's start writing those down. And I'm actually going to move, oh my goodness, I'm actually going to move this one here. Okay, let's actually cut that out. There we go. And I'm going to write the next one down here, which is going to be the derivative with respect to x for cosine inverse of x. This is going to equal 1 divided by the square root of 1 minus x squared. The only difference is that this fraction is negative. All right, so that's the only difference. And this is going to be where, again, the x values fall between -1 and 1. Now, let's move on to tangents. So looking at tangent inverse, we now want to see that the derivative with respect to x for tan inverse of x is going to be equal to 1 divided by 1 plus x squared. These three are some of the most common derivatives that we get to see. They're not only common derivatives, but we also get to see these as integrals as well, as you saw a little while ago. Now, what about the reciprocal functions? So when we're looking at the derivative for cosecant, or the derivative for secant, or the derivative for cotangent, well, we still have to talk about those specific functions as well, and that's what we're going to go ahead and do at this time. So when I look at my derivative, and let's go ahead and let's split this up here. When I look at my derivative with respect to x for cosecant inverse of x, I should be able to extract the result of -1 divided by x multiplied by the square root of x squared minus 1. All right, good so far. We're going to keep going. The next one, secant. So the derivative for secant inverse is going to be very similar. However, this one is going to be 1 divided by x multiplied by the square root of x squared minus 1. There we are, looking pretty good. Now, we're going to work with the last one, which is going to be tangent. So let's look at tangent inverse. Oh, sorry, I meant cotangent. Cotangent inverse of x. Cotangent inverse of next. Cotangent inverse of x is going to get us -1 divided by 1 plus x squared. So now that we get to see these inverse trigonometric values that we then observe, we then want to start talking about, again, their integrals. So the ones on the right, we typically won't see too much. However, when we do, we must know how to take those derivatives for those inverse trigonometric functions. Now, what I was talking about earlier, that we then want to observe these trigonometric integrals. All right, so we know this one trigonometric integral, that's the one that we just observed a little while ago. We're also going to have another trigonometric integral that pops up quite a lot. Nope, let's leave that alone. Whoa, whoa, what's going on? Okay, so cheese and crackers. Okay. Whoa, I have no idea what's going on, everyone. Okay, I finally got the screen to stop squirming. Now, one of the integrals that I wanted to talk about as well was this other integral that pops up quite a lot. And this is the integral for 1 divided by 1 plus x squared with respect to dx. Now, if you look at your derivatives, there's one derivative that stands out with that, and that's on the left side of the screen. So if we were to take an antiderivative of that specific value, then we would be looking at the integral, which would be evaluated to tan inverse of x plus some constant. And again, these are the derivatives of these trigonometric functions that we want to keep at hand. Now, we're going to start implementing this onto our class examples. So on this example, what we want to do is we want to find the derivative and then we're going to simplify wherever possible. Part A. So this is the first example. We're going to work with g of x is equal to cosine inverse of the square root of x. All right, so once we have this, again, we're going to go through the whole process of finding these derivatives. So what I want at this point in time is, again, to take the derivative. So I'm going to apply the derivative here. So the derivative is going to be applied to g of x, and I'm taking the derivative with respect to x. That means taking the derivative on the right-hand side as such. Now, actually, I want to write the argument of cosine inverse a little bit different. So follow me on this. I want to write it as x to the power of 1/2. And the reason I want to do that is because it is easier to take a derivative of x to the power of 1/2 than it is to try to think out loud for the square root of x. So once we have this now, we can then keep going. The left-hand side just turns into g prime of x, so that's not too bad. The right-hand side, however, we need to take the derivative of cosine inverse. So the derivative of cosine inverse, as we get to see at the top of our screen, is going to be -1 divided by the square root of 1 minus the argument squared. Now, what is the argument of cosine inverse? Well, in this case, it's x to the power of 1/2. And then because the argument is made up of a composition of functions, we need to apply the chain rule. That means we still need to multiply by the derivative of x to the power of 1/2. So all we got to do is clean this up. The denominator so far is the square root of 1 minus, this is just going to be x, because x to the power of 1/2 to the power of 2 is just x. And here, the derivative of x to the power of 1/2, now that should be a really good review to taking derivatives from Calc 1. So I would definitely challenge you all to try to take that derivative of x to the power of 1/2. And by challenge, I mean pause the video and see if you can do it yourself. If you can't, that's fine. Just so long as you know how to do it for an exam, you'll be good. So this is what we have so far, and this is the actual answer. All we're going to do is simplify it just a little bit more. That means we're going to multiply some quantities here. All right, so I have -1 divided by Let's go back on that. There we go. 1 divided by, and here I'm going to say 2 times the square root of x multiplied by the square root of 1 minus x. And that's it. This is your final answer. So again, it's looking pretty good. And again, all we're doing is employing these derivatives of inverse trigonometric functions. Part B. Let's work with y is equal to cosine inverse of sine inverse of t. Ooh, that's pretty cool. Okay. So here we go with that one. I want to take this derivative, so once again I am going to apply the derivative onto both sides. So that's going to be dy dx is equal to d dx of cosine inverse of sine inverse of t. Okay, so by the left-hand side properties, we're left with that dy dx is just y prime, so that's great. Derivative of cosine inverse, well, if you look at the top of your screen here, the derivative of cosine inverse, once again, is going to get us -1 divided by square root of 1 minus the argument squared. So that's, again, -1 over the square root of 1 minus the argument squared. Now the big question is, what is the argument for cosine inverse? Well, that argument is just sine inverse. So that's sine inverse of t. Because this is a function composition, I still need to multiply by the derivative of the inside function, and that inside function is going to be the derivative of, wow, I just realized I made a fudge, and I'll show you guys what that is in a bit. My mistake here, is that I assumed that my variable was x. My variable is not x in this particular case. My variable is t. So there's an issue here that I can't say dy dx. I need to say dy dt to be accurate. So dy dt, because t is the variable that we're working with, and this is going to be d dt. Perfect. My apologies for that mistake, but now we can keep trucking on. So let's go ahead and let's find whatever this is going to be. So I have -1 divided by the square root of 1 minus sine inverse of t raised to the power of 2. And then the derivative of sine inverse of t, well, the derivative of sine inverse of t is just 1 over the square root of 1 minus x squared. And this is your final answer. We can combine it just a little bit more, just to make things a little bit more easier, or let's say a little bit more friendly. Because they're not necessarily easier, but they might be a little bit more friendly. There we go. I'm just going to move this a little bit more to the top. There we are. That way I have enough room here to write my y prime, which is going to be -1 over this big denominator of the square root of 1 minus x squared multiplied by the square root of 1 minus sine inverse of t squared. And there we are. So there we are. Everything looks great. And this, again, is that final answer that we're looking for. Awesome. Now, let's see if we can work on part C. All right, so let's go with part C. And again, some of these might get a little bit intense, and that's perfectly fine, because again, it's the nature of what it is that we're working with. So here we have y is equal to tan inverse of x minus the square root of 1 plus x squared, as such. And again, we're going to take this derivative. So once we start taking this derivative, we're going to make sure we go through our inverse trigonometric derivatives. So again, we're going to do dy. Let's check the variable. It's x. So this is dy dx is going to be equal to the derivative with respect to x of tangent inverse of x minus the square root of 1 plus x squared. Okay, not bad. Let's keep going. Left-hand side, that now becomes just y prime. The right-hand side, I take the derivative for tan inverse. So the derivative for tan inverse is just going to be 1 divided by 1 plus whatever's in the argument squared. The argument of tan inverse in this particular case is x minus square root of 1 plus x squared. So that's that. Now I need to multiply this by the derivative of the inside. In other words, I am using the chain rule. So I need to take now the derivative of x minus, and I'm going to rewrite this slightly different. This is going to be 1 plus x squared raised to the power of 1/2. There we are. Whew, that looks intense. All right, let's keep working with it then. So here we go. All right, so here we go. Y prime is equal to, and then we have this piece. So I'm going to expand the denominator as much as I can here. So actually, do I want to expand the denominator? Maybe not. I might want to leave it as is. Okay, so I'm leaving it as is specifically because I want to see where this is going. Okay, I kind of want to be surprised by it. All right, so let's now go ahead and take this derivative. So distribution of derivatives now, I get to take the derivative with respect to x, and that's going to be for the first portion, and then minus the derivative with respect to x for this function of 1 plus x squared raised to the power of 1/2. Now the first term derivative, that's not too bad. That's actually just 1. So I like that so far. All right, so here we go. So that first derivative is just 1, so that's looking pretty good. Let's take the second derivative here now. So I have a minus sign out in the front. That's going to stay out in the front. Okay, power rule, drop the exponent forward. So that's dropping the exponent forward. Keep the argument the same. Subtract 1 from the exponent. That's going to be negative 1/2. And then we multiply by the derivative of the inside. The derivative of the inside is just 2x, so that's what we multiply by, 2x. So again, I use the chain rule to find that derivative. Power rule and chain rule. All right, so everything's looking decent enough so far. So I have my y prime once again. Denominator 1 plus x minus square root of 1 plus x squared, quantity squared, divided by 1. There we are. And on the right-hand side, or what the factor that's multiplying this is going to be 1. And I have a minus. 2's are going to cancel, and we're going to be left with x divided by the square root of 1 minus x squared. That's what's multiplying. Wowzer wowzers. That's pretty intense. That's pretty intense. But you know what? It's looking pretty good. I don't mind it so far. All right, let's keep going. All right, so it's looking okay so far. So I'm going to take my work right up here, and I'm going to continue the work here. So y prime, here we go. Big denominator, that's 1 plus. And actually, I'm going to start expanding this at this point in time because I don't see anything that's going to help me. So let's go ahead and let's expand this binomial. So expanding that binomial then is going to leave me with x squared minus 2x multiplied by the square root of 1 plus x squared. And then we're still going to have plus the last binomial squared. So that's just 1 plus x squared. There we are. So that's the first factor here. The second factor, what I'm going to do is I'm actually going to join this with a common like fractions. So this is now going to be square root of 1 minus x squared minus x, all divided by the square root of 1 minus x squared. There we are. Awesome. So let's go ahead and let's see if we can combine any results together. So combine any terms together. So my numerator is probably going to stay as is. So I'll distribute that in a bit. Denominator, however, I see I have 1 plus x squared, and I have a 1 plus x squared again, and I have a 2 here. So chances are it looks like it can factor. So I'm going to kind of keep that in mind. Okay. So I have a lot of 2's there. So I want to make sure I keep all those 2's. Let's go ahead and let's factor those out. Which means I have 2 quantities of that. So I have 1 plus x squared. All right. And again, I had 2 quantities of those. Minus, I took out this 2. And so now this is x times 1 plus x squared. Square root of 1 plus x squared. That's all in this piece. Now my numerator turns out to be square root of 1 minus x squared minus x. And then denominator, I'm still multiplying by the square root of 1 minus x squared. Okay, that's not too bad. That's not too bad. So let's keep going. Y prime. Numerator stays as is. Square root of 1 minus x squared minus x. Denominator, however, I have a 2, and now this square root of x is going to multiply. So let's go ahead and multiply this square root of x into these specific terms. All right, and so as I'm looking at this, I realize I made a mistake. If you look on the left side on your screen, all the way the very last line, in the big brackets on that denominator, it's the square root of 1 minus x squared. That's supposed to be 1 plus x squared. So that was my mistake there. That's supposed to be 1 plus. So my apologies for that. And I'm making sure that I didn't do some other calculations. It looks like here that messed up. And that's still going to be a minus. So that's not too bad. This one here, that's a minus. Okay, everything else looks good at this point in time. Okay, so let's keep going. 1 plus x squared, there we are. And again, that was this first term. Ah, it actually looks really nice. It actually looks really nice. And I'm going to show you why it looks really nice. What I'm actually going to do for this bracket in the parenthesis, or this terms in the parentheses, I'm actually going to factor out square root of 1 plus x squared from both of these terms. All right, so I'm going to factor that out, and when I do that, I'm going to be left with the square root of 1 plus x squared, and then that's going to be minus x multiplied. Remember, I factored it out. So here's going to be the factor, square root of 1 plus x squared, and then I still have this factor on the right coming out. Now remember, I told you I made a mistake. That one mistake followed me through to the very numerator, and there we are. And this is how I noticed I caught a mistake, simply because my numerator should cancel out with one of the factors in my denominator. So notice this factor and this factor. They're the exact same, which means we're going to get rid of them. So all we're left with is y prime is equal to 1 divided by 2 multiplied by square root of 1 plus x squared. And that's 2 quantities that are multiplying. Hence, it should just be 1 plus x squared. And there's my derivative. Whew! Wow, that was intense. So again, this specific term is this specific term. There you are. Awesome. So again, now that we're taking these derivatives, and again, there goes a lot of algebra and a lot of trig into these derivatives in order for us to be able to take them correctly. So once we are able to grab this, let's go ahead and start with integrals. And let's start looking at these integration techniques using these newfound antiderivatives for inverse trig functions. So we want to evaluate the integral. Part A, this is going to be the integral of 1 divided by the square root of 1 minus x squared and then the denominator is still going to be multiplied by sine inverse of x. And this is all dx. So here's the first example, and we're going to go through it to see if we can find what it is that we need to, let's say, work around. So if we wanted to make a substitution, we have a few options. One of the best options that I can see here is making a u substitution for sine inverse of x. And the reason I want to make it for sine inverse of x is because when I take its derivative, I get 1 over the square root of 1 minus x squared. And this is dx. And that piece, or that factor, 1 over square root of 1 minus x squared, does appear in my integrand as well as that dx. So making that substitution then, I now have my denominator for sine inverse, that's going to be u, but then 1 over square root of 1 minus x squared dx, that's just du, which means all I'm doing is integrating 1 over u du. To integrate this, well, that's just the natural log of the absolute value of u. Since this is an indefinite integral, I choose plus c, and then make my final substitution for sine inverse. Natural log of the absolute value of sine inverse of x plus c. Check that out. That is amazing. That's pretty cool. So that's the first one. That's not too bad. All right. Let's look at part B. So here we go for part B. What I want to do is I want to find the integral of e to the power of 2x divided by square root of 1 minus e to the power of 4x, and this is going to be dx. Awesome. So we're going to work with this, and we're going to see if we can manipulate something. All right. So one of the items that I see automatically is that I can make a substitution first for e to the power of for e to the power of 2x. So if I want to make that substitution, let's say u is equal to e to the power of 2x. Okay, that's not going to be too bad. That means that du is going to be, drop the exponent forward, or e to the power of 2x, that derivative is itself e to the power of 2x. However, the chain rule would drop that exponent of that coefficient of 2. And here we are. Now, the big question might be, well, where's this e to the 2x that I'm making the initial substitution for? Because it's definitely not the numerator. The numerator is actually going to appear here when we're ready to make that substitution. So the substitution is actually finding this hidden gem that we could have the square root in the denominator of 1 minus e to the power of 2x raised to the power of 2. And this is all dx. Check that out. Now the denominator there, that is where I'm making my substitution. That du will then be substituted in for e to the power of 2x dx. That's my numerator. All right, so that's not too bad. I keep going, and this is going to be 1 over the square root of 1 minus the substitution, which is u squared. And then dx is going to be 1/2 du. And again, it's 1/2 because that chain rule brought that 2 down. Now, once we're able to have this here, well, then that's going to be a little bit easier to work with. The half is a constant, moves straight out of the integral. And here we have 1 over the square root of 1 minus u squared. And this is with respect to du. Now we go through and we say, okay, well, what is that integral of? Well, that's going to be sine inverse. So this is now 1/2 multiplied by sine inverse of u. It's an indefinite, so we do a plus c. But what was u? U is e to the power of 2x. And thus, we're left with the final answer of 1/2 multiplied by sine inverse of e to the power of 2x and then plus c. Great, great, great. So it's looking pretty good so far. Let's see if we can take it up a notch. Part C. Part C, I want to evaluate from negative 1 over square root of 2 to 1 over the square root of 2. And this is going to be for the integrand of 6 divided by the square root of 1 minus p squared. And this is going to be with respect to p. Okay, so here we are. Let's look at what we can do. Right away, I start analyzing, and I'm looking that the denominator really stands out to me as, you know, this could be a sine inverse. So that's kind of where I want to go, and I want to start evaluating this for sine inverse. Okay, now I see that 6 is a constant, so what I'm going to do is I'm going to treat that constant as is, and it's going to factor out. And then I have my limits of integration. My integrand is now that 1 minus p squared with respect to p. Now again, some of you might be saying, yeah, that is sine inverse. Well, you're absolutely right. It is sine inverse. So this is going to now be 6 multiplied by sine inverse of p, and this is going to be evaluated from negative 1 over root 2 to 1 over root 2. Okay, that's looking pretty good. So let's keep going with that evaluation then. This is going to be 6 multiplied by sine inverse of 1 over root 2 minus sine inverse of negative 1 over root 2. So we now get to go through that evaluation process and figuring out what this is. Now, if you're going through the whole process and if you're saying, okay, I need sine inverse of 1 over root 2, 1 over root 2 can be thought of as root 2 over 2. Well, root 2 over 2, what angle measurement for sine inverse gets you that angle measurement or that ratio measurement of root 2 over 2? And that should be real nice. It should just be 6 multiplied by, in this particular case, it's just going to be pi fourths. All right, 45 degrees. All right, not too bad. Minus sine inverse of negative 1 over root 2. All right, that one is a little tricky. And it's a little tricky because of this value. Sine inverse only exists or can only be evaluated for angle measurements between negative pi halves and pi halves. The ratio for sine is negative on 2 different quadrants. It is negative on the 4th quadrant, and it's also negative on the 3rd quadrant. So, because of this, the evaluation must be on the 4th quadrant. However, the evaluation must be used for the angle measurement that we're observing, which means sine inverse of negative 1 over root 2 is just going to be negative pi fourths. So what does this mean for us? Well, this means that we're going to be looking at pi fourths plus pi fourths. So that's going to get us what? Pi halves. And then pi halves multiplied by 6 just gets us 3. Oh, sorry, 3 pi. Whew, there we go. And that's our final answer. That's what we get at the end of the day. And this is how we work with those trigonometric functions. Great. So I hope you all enjoyed this, and I will see you all for the next one.